one go.
Okay, so we are happy to have Georg from FZU Prague, and he's going to tell us about boundary terms in open string field theory.
Yes.
All yours, I think.
Okay, so first of all, thanks for having me and giving me the opportunity to talk here. So I will start with giving a short overview over what I will tell you. So first, I will start with some basics of open string field theory, just to know what we are talking about and motivate the problem. And then I will focus a lot on the kinetic boundary term. So this I will divide it in two different ways, like first in a more heuristic way, just using explicit partial integration, and then give a more operator-based derivation, which is more like connected to the operator formalism that we like to have in string field theory. And then I will shortly talk also about the cubic boundary term, the boundary term that comes from the interacting part of the action, and mention some problems that we have with that and why it's not so easy to derive. And then in the end, finish with some outlook and open problems and future directions to work on. Okay, yeah, for the archive number, yeah, it's based on my latest paper, which has this archive number. Okay. Yeah, so first, yeah, we should talk about what is string field theory in principle. So we know if you're working on string theory, usually we have a worldsheet based approach. So we have one worldsheet and we try to compute some things on it. I mean, this worldsheet can be complicated, yes, can have loops, can have whatever, interesting topology, but it's always just one worldsheet. But now consider like collective phenomena, for example. I mean, there are many examples, but like collective phenomena in spacetime, yeah, that involve many worldsheets that pop out of nothing and give rise to a collective behavior. I mean, typical examples are classical solutions, like black holes, let's say, or instantons, or or maybe the most prominent example, tachyon condensation. If a deep brain decays into many tachyons, and the whole system approaches it through vacuum, this has been solved analytically. So what do we need then? We need more than string theory. We need a second quantized theory. We need a theory that allows for many strings. And this is exactly string field theory. And I mean, I can give a comparison, which is, I think, quite useful to understand and why this is interesting. And the comparison is one with GR. So let's consider we have some method that we can compute all graviton amplitudes. And now we say, okay, we know everything about graviton physics, so we want to find out about black holes, let's say. We want to give the full metric of a black hole. Well, to go directly from here to here is probably highly non-trivial, if not impossible. I mean, I do not say impossible, but at least very difficult. Because there's something important missing, which is just the Einstein-Hilbert action. So if we have the Einstein-Hilbert action, then we can go quite easily from here to here, just by expanding the metric into some background plus some perturbation. And we can also go from here to here quite easily just by solving the equations of motion. So let's consider we have some method that we can compute all graviton amplitudes. And this is exactly string field theory. We need a theory that allows for many strings. And this is exactly string field theory. And with string field theory, the story is a bit similar like this. So if we have, maybe I can clean here a bit.
Oh, no, you can use another board.
Oh.
Take that.
So if we have first got the string theory and we can compute all the amplitudes, yeah, then it's still quite non-trivial to go to the things that we have mentioned here, like classical solutions, for example. I mean, there are like background field methods and so on. We can, like, by internal consistency, determine in which background strings can move and so on. But for example, the Tachyon vacuum, we will not find directly just from the amplitudes. And for this, we need string field theory. And this is just similar to gravity. It's an action that gives rise to the string amplitudes via Feynman diagrams. And on the same side, if we want to compute classical solutions of string theory, we can just solve the equations of motion. So this is the reason why I think that string field theory is interesting and a quite essential part of string theory. And now I will, go to the next part, which is to motivate the problem we are considering today. So why we are interested in boundary terms. So, I mean, there are three reasons that I will give. The first one is a mathematical reason that is just needed for consistency. We need a well-defined variational principle for all spacetimes under consideration. This is just necessary for internal consistency. Then there's another point. So we know that string theory contains gravity. And in gravity, we also have a very important boundary term, the Gibbons-Hawking term. So we can expect that the Gibbons-Hawking term should be somewhere there in string field theory. And that's important to know because it's Gibbons-Hawking term is very important for entropy and total energy. So it's important to know where it's hidden in this framework.
But this is just the first reason only, right?
Sorry?
The Gibbons-Hawking term is also needed in GR to have a well-defined variational principle.
Yes,
So
yes.
it's kind of like a...
Yeah, it's related, yes.
Yeah.
Yes, yes. And then there's another argument. So it was shown by Ted Earler just 2 years ago that the onshore action in closed string field theory is actually vanishing apart from boundary contributions. And the onshore action is a quite interesting quantity, and we don't really know what it is yet in closed string field theory. So if we want to understand its meaning, then we have to know the boundary terms, because the boundary terms are the only terms that contribute to that. So this is also an important motivation.
Is that similar to what's happening in general relativity, where we know that the action vanishes in the point because of we have compensation invariance?
Sorry?
Because of
covariance. You mean the Hamiltonian?
Yeah.
I don't think it's at least not directly related. So because this was derived by the Dilaton theorem.
Ted's argument is quite similar in nature.
Ted's argument is based on the Dilaton theorem. I don't know if it uses like time with parametrization invariance.
Yeah.
I don't know. I mean, maybe there's a connection between the two arguments. As I know, like what you're mentioning, the Hamiltonian in those generally covariant systems is just a first-class constraint, right? And that has to vanish. And I don't think that this is the case here, but I'm not sure. I mean, I never, let's say, saw it from this way. So I cannot promise.
Again, the first-class constraint is because of this.
Yes. So, but I don't know if the on-shell action in string field theory is also a first-class constraint. So yeah, those are three good reasons to study boundary terms. And now you might have noticed that at least the second two arguments I gave refer to closed strings and not to open strings. So one might ask, why will I talk about open strings today? So the reason is just that for simplicity, I started with that. And I will talk mostly about the kinetic term. And the kinetic term for open and closed string field theory looks very similar. So most of the results carry over to the closed string case as well with a few modifications. And there was a nice coincidence. That one day after I submitted my paper, there was another paper by Atakan Firat and one colleague of him doing the closed string. It's the same calculation for the closed strings. We didn't know of each other. We did it independently. But yeah, there's of course a lot of overlap between the two papers because, as I mentioned, for the kinetic term, they look very similar. So if you're interested in the closed string case, then you can look at the paper by Sierra Tilmi and I think Raju was the other name.
So related to this third reason, there is another point that you can make is that
yes,
it's if you assume ADS safety, then that also predicts that there has to be a boundary term.
sorry,
If you assume ADS safety,
yes,
so basically on ADS 5 times S5, there is an interpretation of the bulk on-shell action which is in the boundary term, which is the conformal anomaly term. And in the boundary theory, that is a non-zero number, and you can compute that number exactly. And the way to fix it in bulk is to introduce boundary terms, at least at the supergravity level. Okay. So this was something that we did in 22 immediately after Tate's paper.
Okay.
And that kind of already sort of puts some constraint that how, and it's solved at the level of a boundary term, which is kinetic term. So it already sort of puts that there has to be a corresponding completion to the full string field theory such that this boundary term goes to the boundary term in string field theory so that it's consistent with ADS safety.
Okay, yes. Yes, also for sure an interesting point, yes. Sorry, I just take some water. So I think now we're doing the other one. And so, and continue with some basics of open string field theory. So first we have to define what is our basic variable, what should the string field be? And if we just follow the standard approach of second quantization, then the string field psi should just be an element of the Hilbert space of the first quantized theory. And the first quantized theory is usually some boundary CFT representing some deep-range configuration. So we take our basic field that we will take now as a classical field to be an element of this Hilbert space. And then the action that was written down by Witten takes quite a nice and simple form. Namely this form. I will explain all the ingredients in a moment. So what we have here, the Q, is just the BOSD operator. The bracket is the BPC bracket in this boundary CFT here. And the star, this is the most non-trivial ingredient, is the Witten star product. And this has the following very nice interpretation. So let's say we have two strings and want to define a product between those strings. So let's say we have one coming from here and one coming from here. Then what the Witten product does is it takes the right half of the left string, like this, and the left half of the right string, and glues them together here, and integrates over all of the degrees of freedom of those two halves, giving rise to a new string which is combined of the left half of the left one and the right half of the right one. So this is the geometric interpretation of this product. And yeah, this very simple German-Simons type action fulfills everything we need. So it gives rise to all the open string amplitudes at the classical and at the quantum level. And it has gauge invariance. So as I think in any German-Simons theory, we can have if we have delta psi is q of some lambda plus psi star lambda minus lambda star psi, then we can see that there actually is invariant under this gauge symmetry. Yes, so we can deduce the equations of motion. For example, we see for the kinetic term, if we vary this action, we will get, and I will go into more detail about this because it's important for what comes later. So those are the equations of motion. So if we, for example, focus only on the kinetic part here, it gives just the linear part. And this is actually what we would expect because the cube size 0 is the condition for an on-shell state in string theory. And it also has the gauge invariance. So this kinetic part really induces the cohomology of Q as the on-shell states. And the interacting part, yeah, is giving rise to interactions. So this action is what we want and does everything we need. And now let us see how this variation works in detail. So I will start with a very simple calculation, namely I will vary the kinetic term here and see what happens. Let's say I take delta of psi cube psi. Then what I get is
of course, in overall, if you're just interested in the action principle, then of course an overall sign is not important. But you wrote the sign explicitly. Is it because S is now operative definite, or why do you put a minus in there?
Yeah, it's basically a convention. I've seen both conventions. Okay. The minus sign or plus sign.
Okay.
It depends. Yeah, if you want the on-shell action.
I thought you had to keep going.
Yeah. I don't think so. I mean, it's just that the on-shell action encodes the deep brain tension of the whole deep brain, and depending what sign you want to have this, you can determine the sign of the action. But, yeah. I don't think it has a very deep meaning. Okay, so we have delta psi cube psi plus psi q delta psi, right? So, and this we can write as, this is already the term that we want. I can write this as 2 delta psi cube psi. But to do this, we will have to move the q from one side to the other side, and this can and will give rise to non-trivial boundary terms that we will see. So in general, I have an additional term that I will denote as x, which depends on psi and delta psi. And this term x, actually, we don't want for our variational principle. This should be eliminated because we want to, the variation should give only this term here and not the other one. And, well, to compute x, I mean, the first thing we have to do is we need to find the spacetime dependency here, because so far we have written everything just in terms of Hilbert spaces. So we can see just by the explicit expression so that the PPC product actually contains an integral, a spacetime integral, and Q contains derivatives. And if one writes out everything goes into writes out everything in components, then we will find the following two terms which are probably dangerous, which contains derivatives, namely first this one. So I've written a prime here, and the prime just denotes a reduced PPC product where the spacetime integral explicit, just to know where the integral appears. So the PPC product is only everything except for the integral, let's say. And then there's also this term. Yeah, some prefactors which are not super important, but I write them for completeness. Terms are the ones that are dangerous, that contain derivatives. And now we can just proceed by partial integration, and we will find for the total term x the following expression. Well, I write it now as a, as a 25-dimensional integral only on the boundary of M because of our manifold. So this is a normal vector to the boundary, which is contracted in here. It is del mu of psi. Okay, this is what we get for x. We have three terms, and now this we want to get rid of. And usually what we do is so in general, there are two strategies one can do. The first one is very simple and natural, we apply boundary conditions. So the two typical examples are either Neumann or Dirichlet conditions. And we can see by inspection, so for example, Neumann conditions would eliminate this term here and this, but not this one. Whereas Dirichlet conditions would eliminate this one and this one, but not the second one. So both are not enough to get rid of the whole term. And the second strategy is, okay, we can add something to the action to cancel this term. Let's say add some SB such that the variation of SB exactly cancels X. But for this, X has to be delta exact. Otherwise, it's not possible. So we can check actually, no matter if we choose which boundary conditions we choose, this term will be gone anyway. And then we have either this one or this one left. And both are delta exact, which can be checked. So we can add the following SB. So if we have here the zero mode of C del X, then one can check by inspection that its variation exactly cancels these terms here. So this is what we want. And this is almost the final result. So this is like the Gibbons-Hawking analog for open string field theory, at least for the kinetic term so far. So, but maybe we are not totally happy with this derivation because it used those explicit expansions and does not connect in any sense to operator or Hilbert space formalism. So it would be interesting to rederive this term from more fundamental principles. And now let us see how we usually derive those things in operator formalism. So we have seen that in general, psi1 cube psi2 is not equal to cube psi1 psi2. This was the result, basically. And this we can write if we expand the PPC product, then we can write this as an outstate, like the PPC conjugate acting on the vacuum. And then we can represent the U as a contour integration. Of the BRC current. BRC current. And then what we can do is we can just pull off the contour here over the whole worldsheet until it hits this object here. And we have basically proven this relation, which we have shown that is not true. So something went wrong here. And the thing that went wrong, I mean, contour deformation is well established in CFT. It follows from conformal invariance that we can use that. So if contour integration does not work anymore, we know that conformal invariance is violated. And this was a, I think, quite interesting result by Georg and et al., who have shown that explicitly using a path integral derivation that a boundary in target space violates conformal invariance. And now for the rest of the talk, more or less, or for the rest now, I will show how to use their arguments to compute those terms in an operator-based formalism. So what we start with is, we start with the complex divergence theorem to to rewrite our expression. So let's say we have this one. We have the difference between psi1 cube psi2 minus cube psi1 psi2. Okay, can you still read it, or shall I use another pen?
Intro to check.
Yeah. So this can be written in the following way. We can convert this contour integral in a surface integral. So by deforming the contour here from 0 to infinity, we have to cover the whole world sheet. So we can write this as an integral over the whole upper half plane over, no, z here, not x, sorry. And then use del bar of the heuristic current dividing it this way. So now you might say, okay, but del bar of J is 0 because J is holomorphic. But this is not the case anymore if you have a boundary. And the reason for this is del bar of J is non-zero because also del bar of T is non-zero. And this was shown in the following way. So let's say we have an arbitrary correlation function. We know we can write del bar T like in worldsheet coordinates as del A T A B, so which is just a conservation of energy momentum. And let's say we analyze this correlation function, which is supposed to be 0, but let's see what really happens. So we can write it in this way, as a path integral. And then let's take, this can be replaced by the normal ordered product of d of del S Polyakov after del x mu, delta x mu, and a del b of x mu. So this can be checked that if one evaluates this, one gets exactly the conservation here. And then we have the chain of operators which are arbitrary. Okay, and this can be written in the following way. This can be written as a total derivative after delta x mu of sigma of this expression. Oh, sorry, I forgot something very important here. And we have a path integral, of course, we need an exponential of the action here. Yes, so we have a path integral over total derivative. And now let's see what we can neglect here and what not. So we can expand x mu in orthogonal modes. And all the non-constant modes, okay, they will be exponentially suppressed by the action here. But in the Polyakov action, the x only appears derivated. So the zero mode of x mu is not suppressed in any sense here. And the zero mode, it gives just rise to the following thing. It just gives rise to a derivation to an integral over the whole spacetime. and the integral over whole spacetime over the derivation of x mu. If we have a boundary, will induce a boundary term. So this is not zero, but what we will get is the following. It's 2 pi. Then we have a unimportant factor of volume of the worldsheet. This is just from the normalization of the modes. It's not too important. And then we get this boundary term integral over n mu and the correlation function of del b of x mu of sigma, and again our chain of operators. And again, reduced correlation function because the integral is explicit here. So we have shown like conservation of energy momentum is violated, and it leads us, this formula leads us to the following replacement rule. So if we have anywhere like integral over spacetime of del bar t in matter in some reduced correlation function, then it should be replaced by 2 pi this boundary integral n mu of del x mu. It's just follows from converting the worldsheet indices to set bar indices, and this decorative factor here. And this replacement rule we can now use in here, because
You still have time.
Yeah.
sorry?
You still have half an hour, 45 minutes at least. So.
Okay. But, yeah, then. If I have a lot of time, then I will go slower. That's why I ask.
Yeah.
Gave the same talk like 3 weeks ago already, and I was much too slow.
As long as it's not like 3-4 hours there.
Sorry?
As long as it's not like 3 or 4, 5 hours there.
No. Just that I can fill the time also.
Okay, I think the meeting time is from 1 to 3.
Okay, well,
So around,
so you have 1 hour.
yeah, I don't know what's the time now.
It's 3.
Yeah, around 45 minutes.
Okay. So yes, here let us see the first line. We have this del bar of BOSD current, and the BOSD current involves the energy momentum tensor. So using this replacement rule that I wrote down here, we can write the first line in the following way. So we have it closed here because the BOSD current involved has a term C times the energy momentum tensor, so the C survives here. And the del bar of P we replace according to here with a del X. Then we can carry out this integral here. The integral over the plane will just give us the zero mode of this object. And this is, and this expression.
Guillaume, can you remind me how did you find
Yes.
I'm a little bit, how did you find that t derivative of t is the action derivative of the action normal or
Yes. Well, this can be shown by using the explicit form of the Fourier conversion, the explicit form of the energy momentum tensor. Then you see that this object and this is the same.
Is t is this what's called if we're doing Bulletproof action, then we could
Yes.
vary in respect to the world shape metric. So usually t is
It's the variation of the action. Yes, yes.
the
But
world shape. I don't see any world shape metric here.
no, I mean the vertex metric I think here is in conformal gauge fixed
Right.
to.
So you're
Cool.
claiming that this gives the same.
Yes, yes, yes. Yes, this is my claim. Yes, I don't know if I can do the calculation now in Scratch, but I think it's 2 lines or so. It's not hard to show.
And then you integrate by part, that's t.
Yeah, yeah. Yeah, so what we get by carrying out this integral here is the zero mode of c del x. And we see the zero mode of c del x already appeared here. So it's good news that we are on the right way. And so this is what you would get for the more or less for the boundary term x, but we are not done yet. I mean, this is not the final answer. And the reason is the following. So as it is written now, this object here, this operator is acting on the psi 2. But we could have as well started the whole calculation from the other side. We could have written this difference here in the other way around, this whole thing acting on the psi 1 instead of the psi 2. By the way, here for and then what we have gotten here is the whole thing acting here and not here. Now we can ask, is it the same? And it's not the same. It's not the same for the same reason as because we have a boundary in spacetime, and this involves a derivative, and it matters where the derivative acts on, if it acts here or here, because we cannot do partial integration like arbitrarily. So actually we can go through, I will not discuss all the technicalities here, but we can use a similar argument to this one to show that the only way to make the thing consistent is if this operator acts symmetrically on the psi 2 and the psi 1. Otherwise, we would not get the same result for this difference if we turn it around with a minus sign. So this thing here has to act symmetrically. And if we do that, and then also just replace psi 1 by psi.
What does the zero subscript mean?
Zero mode of this
Oh,
object, of the whole combined operator. And psi 2 to delta psi, and then insert this with the symmetrization that I just discussed, then we will get exactly this here, this term here. And we have seen that this term can be cancelled by this term here, by this by this Gibbons-Hawking-type term. So in the end, it succeeded that we have rederived this term by a more operator-based formalism using the breaking of conformal invariants. So yeah, so this was basically all about the kinetic part. So let me now discuss the cubic boundary term. So I have not prepared too much to this because what I did in the paper is very technical, so I will more discuss the conceptual issues.
But before you move to cubic, can I ask?
Yes, yeah, sure.
So one thing is that as a formal derivation, I can understand this, it pretty much goes through. But for open strings, strictly speaking, we would not expect any Gibbons-Hawking-like term, right?
Yes, yes. I mean,
because if I just look at the, let's say, the low energy effective action, it's just some gauge fields, tachyons. The kinetic terms for these are, we can derive them using the open string field theory, and it looks exactly the standard kinetic term, and all of those variational principles are well defined. Like unlike the gravity, where you have derivatives of the Riemann tensor appearing.
yes.
You have two derivatives of the metric field appearing, so you need to include a Gibbons-Hawking term to make the variational principle well defined.
Yes, but I think in general, like the low energy effective action that you get, for example, for closed strings, I mean, this was also done in the paper by Atacam. Like string field theory gives gravity in the low energy expansion, but only up to boundary terms.
Yeah, that I agree. I mean, like for the closed strings, I know that you can get the linearized Einstein-Hilbert term, but even the linearized Einstein-Hilbert action is not well defined as a variational principle unless you also include the linearized version of the GHY.
Yes, and I think something similar happens here. So if you expand in the
But that's what's puzzling me. I mean, with the low energy effective action of this is tachyons and Young-Mills.
Yes, but for example, for the tachyon, you will get.
I will get like say pi box phi, right?
Yes, you get phi box phi, but phi box phi needs a boundary term to be well defined in the variation principle, because phi box phi is not equal to d mu phi.
Yeah, it's off by.
So this here is okay with only boundary conditions. For this here, you need both. You need boundary conditions and some extra term to make it well defined, because the two derivatives are in the same place here. I think this is the reason. Yes. So also for the open strings string field theory, by expanding it does not give rise to the standard kinetic term, but to this one.
But isn't that just a choice? Can you just write it as in the first order instead? I mean, isn't that just because you have the Q and inside Q sits T, and now you want this to be a box, but you could maybe rewrite it a little bit. So the boundary term is probably just undoing this writing.
Yes, the boundary term comes because in this kinetic term we have here.
Yeah.
Because
you insist on the Chern-Simons form.
Because you insist on the Chern-Simons form. You don't want to split the Q apart
in two parts.
Yes.
But you could do that, and then everything probably would be fine.
I don't know if you could do that, because Q is like a nice operator with nice properties, and you don't want to tear the Q apart, and maybe you would introduce some nasty properties.
Yeah, but I think if you formally just do it anyway, then I think that's exactly.
Yes. I mean, if you formally just do it, then you would undo the boundary term. Yes, I would agree. Yes, but I don't think it's like convenient to do that. But I never thought about it, so maybe.
I mean, all the effective kinetic terms are typically always of the form psi, B1 psi or L1 psi, etc.
Yes,
right?
yes.
It's,
Okay, so yeah, then maybe I can erase this here or the other one. Erase here and discuss the cubic term in a minute. So again, I mean, usually we have this relation for the cubic term called the cyclicity relation that we can permute the psi cyclically.
Sorry, Georg, I had one more question.
Yes.
This boundary term for the free theory that you write down, and it's also gauge invariant, it doesn't.
No. Gauge invariance is an interesting topic. So it was discussed more in Atakan's paper.
Yeah.
It's not gauge invariance. Basically, you have to fix the gauge on the boundary. This is required. Because this term here, the C that X mu term is not gauge invariant. Or only we only have a subgroup of gauge transformation which leave this environment. Yeah. So usually you have this relation, but again, in presence of a boundary, we would expect that this is violated. And this would lead also to a cubic boundary term, because if we vary this, we want to move the delta to, let's say, the first position. And actually, the x cubic that you would get, if you compute the difference here, I did the computation in the paper. It's quite technical, so I will not present it, but I will just describe the difficulties associated with it. So let's say we just focus on the tachyon field only, on the tachyon T of x, and compute this thing here, T of x star T of x. And this thing can be computed, and it's proportional up to some unimportant prefactors to an integral of this object e to the minus alpha prime logarithm of 4 or 3 times kernel of 3 box acting on T of x in the whole thing to the third power. So this is non-local. We have infinitely many derivatives appearing here. And this makes it very complicated. So, for example, one can just expand this, let's say, to second order, and you will see that only Neumann or Dirichlet conditions alone are not enough. You need more boundary conditions, and in principle, although this is not always true, but by naive counting, you would assume that you would need infinitely many boundary conditions to make such a thing well defined. This is not always true. I mean, there have been papers about that, but at least the typical boundary conditions that we apply are not enough. And now the question is, okay, is the remainder something delta exact, something that I can cancel? And in my paper, what came out is that it's not the case. And okay, what's the reason for that? So maybe the whole thing doesn't make sense in these things. So what we want to do now is to have a sharply located boundary in a non-local theory. And maybe this just doesn't make sense. Maybe this is just inconsistent. And one thing that I think is interesting is, instead of a sharply located boundary, one can study the whole thing for an asymptotic boundary. So in the sense of some Penrose-type compactification, because then you don't, instead of boundary conditions, you have fall-off conditions, which maybe offer more variety, and those things maybe can be solved. And this is, I think, a very natural follow-up project. So this would be the next step to do or to study, and maybe I will do this in the future.
It seems to me that before we get to boundary terms in orbital field theory, it sounds like one have there been papers written on boundary terms in non-commutative geometry in field theory?
Non-commutative geometry?
Not geometry, in non-commutative field theory.
Non-commutative field theory.
So where you have a Moyal star problem.
I see.
So I suspect it's more or less the same, right? I mean, where you also get the formula you wrote there with infinitely many derivatives.
Yes.
I suspect that something similar happens in non-commutative field theory. And there might be people who have thought about that.
Maybe I don't know what I have to say. I know there is a connection between the Witten star product and the Moyer product. I think there are papers by Itzhak Bars, as far as I remember. Yeah. So that they are related, but I don't know if, like in this case of non-commutative geometry or non-commutative field theory, they ever anyone thought about boundary terms yet. But it's a good point. Maybe
I mean, check it out. When I say non-commutative field theory, I mean in the sense of Witten.
In the sense of
what I mean during the Witten back in then they had a paper on this, right? Non-commutative in that sense.
Yes.
In field theory.
Yes.
Which I think is a little bit different from non-commutative geometry of Coulomb.
Probably yes. I'm not an expert on this, I could say, but like theories involving the Moyer product might be interesting because, as I said, there is a relation to this product. So yes. Yeah, basically, I mean, this discussion already brings me to the outlook. So,
Georg, is there, can it be something alternative? Like, for example, instead of working with Witten's cubic, if we work with the infinity version, and let's say that I have modified or I have fixed the variational problem of the kinetic piece by introducing this term.
Yes.
And then if we impose that there is the infinite relation still continues to hold. Does that induce enough structure or enough constraint to fix at least some form of the A2, A3, A4, so on? Because naively speaking, if I take a kinetic term and I replace it or by add another sort of boundary term of two derivatives in it, typically the infinity structure might not be satisfied anymore.
Might not be satisfied anymore. No.
So I might need to sort of modify the A2 products, A3 products, such that and that might give me a sort of bootstrap. Might not determine it uniquely, but it gives some constraint that how.
Yes, I mean, okay, this is also like tied to the question about gauge invariance before. And,
exactly.
I mean, if the infinity relations were satisfied, then the whole thing would still be gauge invariant. And still, we know that this is not the case. I would say that this boundary term violates already the infinity.
Yeah, but I mean, I'm thinking in the sense that like this A infinity gauge invariance, a subset of that, the gauge invariances that we want the theory to have. Like, for example, it includes Young-Mills, or it includes higher versions of those gauge symmetries. So it's not a good thing that it gets violated by adding some boundary term, right? We would want the full theory to have that. So
yeah, I mean, in some sense, yes. I don't know if it's a problem if we like put a restriction on the gauge symmetry on the boundary and say, okay, gauge symmetry only holds in the bulk, and on the boundary something has to be fixed. I think this still can be consistent. But I mean, it would be, let's say, more beautiful or more appealing if it still holds, yes.
I mean, if you are putting certain conditions on the boundary, then essentially you are disallowing certain gauge transformations already, right? I mean, there is a subset of gauge transformation which you're now saying that it's allowed.
Yes, I mean, I'm just thinking about what happens in GR. I mean, you still have diffeomorphism invariants, but only those which keep the boundary fixed, right? For the Gibbons-Hawking-type. So you also restrict the gauge transformations in some sense. And maybe something similar happens here, that just a subset of gauge transformation survives for the full action.
Yeah, I'm just a bit worried because I mean, if this would be in some way in conflict with the full BV construction, because I mean that is quite crucial in sort of reproducing or connecting it with the string wall sheet computation, right?
Yes.
Like the fact that this is a nice, at least classical BV action was used by Witten to show that you have the full decomposition of the moduli space, and then you can reproduce all the strings, at least 3-level string, open string scattering amplitudes from this.
Yes.
So if that is somehow being curtailed, it's probably not a good thing. What could be consistent is that, I mean, you add boundary terms and then you sort of, it's not enough to add a boundary terms at tree level, but you need to add something at the cubic, and if it's a infinity at quartic, so on and so forth, such that the whole thing as a whole kind of makes sense.
Yes, I mean, this is expected. I mean, even just from this form, you see like that partial integration will give rise to boundary terms. So
Yeah.
it's expected that also for our closed strings that every vertex will produce some boundary
Yeah.
term if there is a boundary.
Yeah, I mean, it has to, because the GHY is quite
Yes.
non-linear itself.
Yes, yes. But if one can still satisfy some A or L infinity algebra, if you include all those boundary terms, I don't know if that's possible. Maybe not, because at least those simple results here indicate that maybe it's not possible. But I don't know how this can be made gauge invariant. I mean, I did not think about it for a very long time, but it's certainly an interesting point, yes.
Okay.
Okay, so I mean, this is gauge invariance, and analyzed gauge invariance is also one point that I put into the outlook section. So this we discussed just. So I mean, I talked already about the asymptotic boundaries. This is also a very natural way to continue the work. I mean, then what I mentioned in the beginning is the on-shell action equals SFT. Because we still don't know what it is. So like for the open string, we know that the on-shell action is an important quantity because it's a deep-point tension. It's the deep-point tension, the tension of the deep-point that can decay into a tachyon vacuum. So it's a physical quantity which is of importance. But for closed string field theory, we don't know yet what it is. And there are some proposals. So there is one proposal that in the gravity sector it corresponds to the ADM mass, which is somehow interesting because we have seen that it receives only contributions from the boundary, and the ADM mass is also computed on the boundary, so this would somehow fit together. And now that we have the boundary term at least for the kinetic part available, maybe this can be checked, or at least more motivated, or how to say, or show that it's not true. I mean, then there's also a proposal that it might correspond to some defect by combining the defect in the CFT, and there are others as well. So we don't really know what this is yet, and knowledge of the boundary terms might us enable to find out more about this very important quantity. And then also one more outlook that one can do is to analyze different backgrounds. So for now, I mean, I did the whole thing just for flat spacetime, flat 26-dimensional spacetime, without any additional fields or anything. But for example, people are also interested in linear dilaton CFTs. They are appealing mostly from a closed string perspective, because in closed string SFT we have the ghost dilaton, which is quite a nasty thing that you cannot set to 0, but in a linear dilaton background you can set it to 0. But a linear dilaton has the property that it goes from -infinity to +infinity, so it's not normalizable as soon as you don't put the whole thing in the box. And if you put it in the box, then boundary terms become important. So if one wants to work in a linear dilaton background, then it's expected that you need the boundary terms. Yeah, I think that's all I wanted to say. Maybe I was a bit short this time. Last time I was too long. I hope it's okay. So thanks for the attention.
Thank you. Thank you. Do we have more questions?
You mentioned briefly closed string theory. Can you say anything more about the corresponding calculation in closed string theory?
Yes, the corresponding it's in some sense very similar. The only difference in closed string field theory, the kinetic term looks like this. Well, let's use a different letter. I mean, first, of course, the closed string field has both sectors like holomorphic and anti-holomorphic. But apart from that, the closed string kinetic term looks like this. You have an additional insertion of C naught minus, which is necessary to fulfill the ghost number constraint, because a closed string field has ghost number 2. So we have ghost number 2, but Q has still ghost number 1. So it only adds up to 5 and not to 6. So one needs an additional insertion here. But this is already all the difference. So the difference is just that we will live in a different Hilbert space with 4 sectors and have this insertion here. And apart from that, the calculation is basically the same. So in the end, you would get a similar thing to here. Maybe you have like C del x and plus C bar del x bar and so on to add for the anti-holomorphic sector, and you have this additional insertion. And for the interacting part of closed string field theory, so in closed string field theory you have infinitely many vertices and not just one. And there are no results available yet. So in the paper by Atakan and his colleague, they only did it for the kinetic part.
But I guess you would like to see the Gibbons-Hawking your term come out somehow.
Yes, I mean the thing is it does not precisely come out, and on linear level it does not precisely come out, and the reason is because closed string field theory is equivalent to gravity on the nearest level only up to boundary terms. So you already have a difference in boundary terms. And this is why you cannot reproduce it exactly. So you can check that, let's say that the sum works out. So if you make closed string field theory consistent from a variational principle, then its boundary term is just the sum of Gibbons-Hawking and the difference between gravity and closed strings, which is basically a consequence of the uniqueness of the Gibbons-Hawking term. So this works out, but they are not totally equivalent.
Is there a way of connecting with this what Ahmed Ahmeden and Aaron Wall, these people are doing using Saitlin's approach to spacetime action? Because they claim to have some derivation of the linearized Gibbons-Hawking.
Yes, I mean I vaguely remember something like that. There was a talk in Benasque last year about that, but I don't remember exactly. But they had some different answers. I think they used these background fields arguments with the vanishing beta function and this. So it was somehow different approach. Yes,
it's a completely different approach, you know.
Yes,
but they seem to have a. But another thing is that about the second point in the outlook, this on-shell action in closed string field theory. Once again, I mean, I think the AT is 5 times S5 is a very good test case. Like if you, of course, it's an assumption that AT is 5 times S5 is an exact string background, but I mean, it's a reasonably good assumption. In that case, the on-shell action of the type 2B string on this background is precisely the type 2B supergravity action. Because all the other things on-shell value are 0, exactly. So you have the metric, you have the Raman 5 from flux and the dilaton, that's it. And that on-shell action has a sort of interpretation. I mean, it gives you basically the regularized volume of the ADS5 factor. So that is definitely not the ADM mass or can be related to a defect or anything. It has an interpretation in terms of the dual boundary theory. But from the bulk side, it just looks like a volume of the ADS5 with a precise proportionality constant. It's a number. So I guess that's already sort of giving one hint that what kind of thing this on-shell action is. So
Okay, yes,
it
yes.
just hinges on the assumption that, okay, I mean, we are assuming that the spectrum is an exact string background, but I mean, for that we have enough evidence to
Yes, okay.
strongly believe in that. So yeah,
Yes, I mean, it might change something if you consider full superstring field theory and not just the bosonic part.
no, I mean, even if you consider the full supersymmetric string theory, you just have the full supergravity solution is known, right? And then it's conjectured that this is the exact solution. There are no more alpha prime corrections, no more G string corrections, and that's it. So this is the strongest form of the idea safety. Like it's the full string theory which is dual to the n equal to Bose-Einstein. It's not just supergravity.
Yes.
So based on that, I think there is already an interpretation of, at least in that specific case, what the optional action is. It just, yeah, and it doesn't. I mean, it has nothing to do with the ADM mass or the defect.
Yeah. Okay.
So, yeah.
Okay. Yeah. That's an additional point to add here. Yes. Okay. Thanks.
Yeah.
If there are no more questions, then thanks to the speaker again. Now it's